So in this video we'll be going over sample questions from chapter 6, and we'll be dealing with chemical reactions and balancing the chemical reactions, and then we'll also be solving equations for solving for the molar mass of compounds and using those combining those concepts by using balanced equations and be able to go from reactants to products, so determine how much product was made from a known amount of reactants and vice versa. So we're going to start off by going over just balancing out these chemical equations. So in the first one we'll do is 6.3, and we'll do letter B. And so what I suggest you to do is to write out the different atoms or different elements found in the equation. And we find Hg, which is mercury, and O for oxygen. And on the reactant side of the equation, we see there's one mercury and one oxygen. And on the right hand side, we see there's one mercury and there's two oxygens. So we see that these numbers are not balanced. So we need to figure out what we need to do to balance these out. And so we see that the discrepancy here is coming from the oxygen. And so somehow we need to multiply this by 2. And so if we multiply our oxygen by 2, we'll need to put a coefficient in front of the 2 in the equation. And so if we do that, that coefficient 2 is distributed to not only the oxygen, but also the mercury, the Hg. So if we put a 2 in front of that mercury oxide, then we'll also be multiplying the mercury by 2. And so now we have 2 mercuries and we have 2 oxygens. But now that leads us to another inequality. And here we find that there's 1 mercury in the products and 2 in the reactants. So we need to multiply the mercury by 2 to balance it out. And so in order to do that, we need to put a 2 in front of the mercury. And in doing that, that will multiply the mercury by 2. And since it's just mercury by itself, then there's nothing else that's going to be affected. And so here, now we have a balanced reaction. And so here we have 2 mercuries and 2 oxygens in the reactants, and we have 2 mercuries and 2 oxygens for our product. Doing another equation, we have to balance this chemical reaction in 6.5, letter A. And this is very similar problem. The main difference here is that we're using polyatomic ions. And so we mentioned that in the previous chapter. We didn't really deal with it too much. But the only thing that we're going to do, we're just going to treat these polyatomics as essentially as atoms, as we had done in the past problem. And so here again, if we're doing a balanced reaction, we want to write out all our parts together. So we have magnesium, we have silver, Ag, and instead of breaking it up, the nitrate, the NO3, we're going to keep it together. So we're just going to use it as NO3. And we're not going to break it apart because NO3 we see in the reactant side is kept together here, and it's also kept together in the product. So there's no reason to break it up into nitrogen and oxygen parts. So in the reactants, we see that we have 1 magnesium, we have only 1 silver, and we have 1 nitrate group. In the product side, we have 1 magnesium, we have 2 nitrate groups, so that 2 outside the parentheses distributes to that whole part in the parentheses. So we have 2 nitrate parts, and we have 1 silver. So right off the bat, we see that we have a discrepancy, we have an inequality within the nitrates. So we'll have to multiply the nitrates by 2. If we want to do that, then we'll have to multiply the whole compound that contains the nitrate. And so we'll put a 2 in front of the silver nitrate. So that coefficient of 2 is distributed to not just the nitrate, but also to the silver. So the silver is going to be multiplied by 2. And so now we have an inequality with these silvers. And so the silver is now 2 for the reactants, only 1 in the product. So we need to multiply this by 2 to get it to equal 2. And so in order to do that, we'll have to put a 2 in front of where we see silver, 2Ag. And there's no other part to the silver metal, and so now it appears that our reaction is balanced. So here we have 1 magnesium, we have 1 magnesium. We have 2 silvers, 2 silvers. We have 2 nitrates, because that 2 is distributed to the NO3 group, so that's 2 nitrates, and we have 2 nitrates. And so now our reaction is balanced. All right, and so here we'll look at we also discussed redox reactions or oxidation-reduction reactions, and so here is our job to figure out which reactant is oxidized and which is reduced. And so remember the saying oil rig. So oil oxidizing is losing. Reduction is gaining. And so what they're referring to as losing and gaining is that we're losing electrons in oxidation. And so in oil, oxidation is losing. That means it's losing electrons. And so if it's losing electrons, it's losing its negative charge. And so if it's losing its negative charge, it's going to either get less negative or more positive. And the rig part, reduction is gaining electrons. And so if you're gaining electrons, you're gaining negative charge. Electrons are negatively charged. So you're getting more negative or less positive. So it's our job to figure out if these species are negative or positive. And so in B, chlorine, when we have atoms by themselves or in their natural state, then their oxidation number, basically their charge, is 0. So in the reactants, Cl is equal to 0. Going back from the previous chapters, remember that group 1 metals such as sodium in compounds likes to take the charge of positive 1. And so that's what it actually is here. Sodium is going to have positive 1, and bromine is a group 7A element, and so it likes to take in an electron, so it likes to have a negative 1 charge. And so then we look over at the right hand side. All right, now we have sodium still in a compound, and so sodium is going to remain a positive 1. All right, it's a group 1 metal. When group 1 metals are in compounds, they're typically going to take a positive 1 charge. Chlorine is no longer by itself, so it's in a compound, and so it's a group 7A element, so it's going to want to take in a negative 1 charge. Actually, we're going to move that over here. And then bromine is in its natural state. It's all by itself, and so bromine now has a 0 charge. So here we're getting more negative, and so that is going to be gaining electrons. And so that's going to be the rig part. So that's reduction. So gaining electron. And so chlorine, so Cl2, is being reduced. And here, the bromine is going from negative 1 to 0. And so the bromine is losing electrons. And so then the Br minus is being oxidized. And so that's how you do 15b. Okay, so now we are going to move to 6.21, and in these questions we have to use Avogadro's number. All right, so Avogadro's number is used to determine how many pieces there are to the whole. So how many atoms in a mole, or how many molecules in a mole. So it's bringing things in reference to moles. All right, and so the Avogadro's number is equal to 6.02 times 10 to the 23rd parts, whatever you're talking about, atoms, ions, molecules, whatever you have, per mole. And so we can use that conversion factor in any way we need to. And so if we have, it wants us to determine how many atoms in 0.20 moles of silver. And so here we want to go from moles to atoms. So our answer needs to be in atoms. And so if we want our, and we have 0.200 moles. So in this equation, we want our moles to cancel out. And so if we want our moles to cancel out, then moles has to be on the bottom here, so they can cancel out. And what is left is the atoms on top. And that's going to be our 6.02 times 10 to the 23rd, our Avogadro's number. So all we're doing is taking the 0.2 moles and multiplying it by Avogadro's number. And so when we do that, we get 0.2 times 6.02, 0.2 times 6.02 times 10 to the 23rd. Calculator malfunction here. And so we get 1.20, we can report three significant figures, times 10 to the 23rd atoms. Okay. A very similar question. We're going to again use Avogadro's number, but here we want to go from atoms to moles. And so here we're given 3.26 times 10 to the 24th atoms. And we want our atoms to cancel out because we want our answer in moles. So atoms would cancel out. And so what we're going to use is we're going to use the inverse of the Avogadro's number. So 6.02 times 10 to the 23rd. And so when we do that, we get an answer of, let's see, 5.42. 5.42 moles of aluminum. Okay, and so we'll move on to the next one. Alright, so here it's asking us calculate each of the following quantities in 2 moles of phosphoric acid, H3PO4. And so here we're just using mole-to-mole ratios within the compound itself. And so in A, all right, we are trying to go from moles of H3PO4 to moles of hydrogen. Okay, so we have 0.200 moles of H3PO4. We want our answer to be in moles of H. So looking at our H3PO4, it says for in one molecule of H3PO4, there are 3 hydrogens. So here, and the same thing goes with, if we have 1 mole of H3PO4, then we have 3 moles of hydrogen. So here we want our moles of H3PO4 to cancel out. So that's going to go on the bottom. So in 1 mole of H3PO4, move that over, we have 3 moles of hydrogen. And that just comes from the formula itself. And so here, 0.2 times 3 is 0.600 moles of H. The same thing can be done for B. And so in B, we have 0.200 moles of H3PO4 again. And this time we have 4 moles of oxygen per 1 mole of H3PO4. And that just gives us 0.800 moles of oxygen. Then we can just do one more. We'll do D. We'll just skip to D. So we already had found out how many moles of oxygen we have. And so now we're asked to solve the number of atoms. And so we're just going to here just go one step further and use the Avogadro's number. And so we have 0.800 moles of oxygen. We want to get to atoms of oxygen. So here we want our moles to cancel out of oxygen, and we want atoms as our answer. And so we said before it's 6.02 times 10 to the 23rd atoms per mole. And so then we go calculate it out. 6.02 times 0.8, and we get 4.82 times 10 to the 23rd atoms of oxygen. Okay. Now we're getting into molar mass. So molar mass is by definition the mass of an element or compound with 1 mole. So 1 mole of this compound or element, and what is its mass? So we'll do B. So here it says that we have Fe2O3. And so if we have 1 mole of Fe2O3, Fe2O3, then we have a mole to mole ratio of, we're going to solve for how many moles of iron we have and how many moles of oxygen we have. So here we want to get moles of Fe. And we want our Fe2O3 to cancel out. So here we look at the equation. There's 2 moles of Fe per 1 mole of Fe2O3. And so that's 2 moles of iron. Then in 1 mole of Fe2O3, there's going to be 3 moles of oxygen per 1 mole of Fe2O3. And so that's 3 moles of oxygen. And so now we have to use our periodic table. And so we go onto our periodic table and we find iron with atomic number 26, and it says that 1 mole of iron has a mass of 55.845 grams. So if we have 2 moles of iron, then that would weigh, we would multiply it by its molar mass. 55.845 grams of iron divided by 1 mole of iron. And so there we get a number of, let's see, 55.845 times 2, 111.7 grams per mole. Well, they actually gave 6.9, so we'll use 6.9 grams. And for oxygen, we have 3 moles of oxygen, and that is multiplied by oxygen is atomic number of, I didn't even show the iron. Oxygen has an atomic number of 8, and that's 15.999 grams per mole. And we get 47.997 grams. Sorry if it's not clear. And so now we just have to add them together to get Fe2O3. So we're going to add 111.69 plus 47.997, and we get a number of 159.69 grams per mole. And that is the molar mass of Fe2O3. So we just have to use the mole ratios within the chemical formula, and then use the molar masses to determine the molar mass of the whole compound. All right, and so we'll be using that in future calculations. So that's just part of, usually you're not asked to find the molar mass. Usually you're going to be asked to use the molar mass to find out other information. So here it's asking us to calculate the mass in grams for each of the following compounds. So in A, we have sodium chloride. Sodium chloride has 1 sodium and 1 chlorine. So sodium is atomic number of 11, and so it has a molar mass of 22.990 grams per mole. Chlorine, atomic number of 17, has an atomic mass of 35.45. There's only 1 of each in the compound, NaCl, and so for 1 mole of sodium chloride, we would have NaCl would equal 58.44 grams per mole. And here it says we have only 0.5 moles. So if we have 58.44 grams per mole for NaCl, and we only have 0.500 moles, if we only get a half a mole of NaCl, we would only have 100, no, went the wrong way. 29.22 grams of NaCl. So now we have just calculated the number of grams from a given number of moles of a material. Now we are going to be asked to do the reverse. So given a number of grams of material, how many moles are present? And so here in 6.39, we'll look at letter A first. It asks us how many moles are present in 50 grams of silver. And so we have 50 grams of silver, and we want to go and figure out how many moles of silver we have. And so in order to do this, we need to have our grams of silver cancel out, and we want moles of silver. And so here we're going to use the molar mass. And so if we go to our periodic table, we find silver. Silver has the atomic number of 47, and so its molar mass is 107.87 grams per mole. And so it's 107.87 grams per 1 mole of silver. And so we're going to essentially take our 50 grams and divide it by 107.87. And we get a number of 0.464 moles of silver. And so that's how we solve that. And now we can do another one. We can look at C. That was just for an element. Now in C, we're looking at a compound. And so that's A. And so now C. So before we get to do our first calculation, we need to figure out the molar mass of ammonia, NH3. And so nitrogen has a molar mass of 14.007. Hydrogen has a molar mass of 1.0079. And there's 3 of those in NH3. And so we get 1.0079 times 3, and we get 3.0237 grams per mole of H3. And so now we just have to add those two numbers together. And we get NH3 is equal to 17.0307 grams per mole. And so if we have 15.0 grams of NH3, we want our grams to cancel out, and we want moles. And so we have, in 1 mole, we have 17.0307. And so 15 divided by 17.0307, we get 0.881 moles of NH3. Okay, and so 6.41, it's asking a very similar question. We'll just skip to letter C. All right, and in letter C we have Al2S3. And it's asking just for moles of it's being specific to silver. And so in Al2S3, we need to first figure out its molar mass. And Al has a molar mass of 26.982 grams per mole. And silver has a molar mass of 32.065 grams per mole. And so we're just getting those numbers from the periodic table and using their average atomic masses and molar masses. And so we have 2 in Al2S3 and 3 silvers in Al2S3. And so we first multiply those numbers. So 26.982 times 2, we get 53.964 grams per mole. And for sulfur, 32.065 times 3, and we get 96.195 grams per mole. And we're going to add up those two values, plus 53.964. And we get a number of 150.159 grams per mole. So first we need to figure out how many moles of the compound we have. And so here we have 30.1 grams of Al2S3. And if in 1 mole of Al2S3, it would have a mass of 150.159. So we take 30.1 divided by 150.159, and we get 0.200 moles of Al2S3. And if we have 0.200 moles of Al2S3, then we have to use our mole ratio. So in 1 mole of Al2S3, we have 3 moles of sulfur, and that comes from the chemical formula. And so we just need to multiply that by 3, and we get 0.600 moles of sulfur. All right, now moving on to question 6.43, gives us the formula for caffeine, which is C8H10N4O2, and it's we'll go through A through D, and it's asking in A how many grams of caffeine are in 0.85 moles of this caffeine. So the first thing we'll need to do is first figure out the molar mass of caffeine. So the molar mass of caffeine, you have carbon, and carbon has a molar mass of 12.011. We have hydrogen as 1.0079, nitrogen as 14.0067, and oxygen 15.999. And we have 8 carbons, we have 10 hydrogens, we have 4 nitrogens, and 2 oxygens. So we just need to multiply these and then add them all together. So 12.011 times 8 is equal to 96.088. For hydrogen, it's 10.079. For nitrogen, it's 56.0268. And for oxygen, we get 31.998. And so we add all those together. And we get a molar mass of 194.1918 grams per mole. All right, and so here it's asking in A how many grams of caffeine are in 0.85 moles. So we're trying to start with 0.850 moles of caffeine. We need to multiply by something to get the grams of caffeine. And so we want moles to cancel out, and we want grams to be left over. And so in 1 mole of caffeine, it would have 194.1918 grams. And so you just multiply those two numbers, and you get 165 grams. And so we can report 3 significant figures. And then in B, it's asking how many moles of caffeine are in 28 grams of caffeine. And so here we're starting off with 28.0 grams of caffeine. We want to go into moles, so we want our grams to cancel out, and we want moles to be left over, and we're just going to use the inverse now. So 1 mole has a mass of 194.1918. And we get number of moles of 0.144 moles of caffeine. And then looking at C, it's asking how many moles of carbon in 28 grams of caffeine. And so we just solve for how many moles of caffeine we have. All right, so we can base our C and D off of part B. And so in C, if we have 0.144 moles of caffeine, we want to get moles of carbon. And so we just have to use the mole ratio, or mole to mole factor, or whatever you want to call it, from the chemical formula. So caffeine was CaH10N4O2. So in 1 mole of caffeine, you would have 8 moles of carbon. And so we just have to take our moles of caffeine and multiply it by moles of carbon, and you get 1.15 moles of carbon. And then similarly in D, if again we have 28 grams of caffeine, so that was already solved for, that's 0.144 moles of caffeine. And in terms of nitrogen, in 1 mole of caffeine, we have 4 moles of nitrogen. And so here we get a number of 0.577 moles of nitrogen. All right, moving on to 47. It's asking us, we're given this reaction, and so here we're kind of using it from a lot of what we've gone through with this whole chapter. We're kind of putting it together in the last part of this chapter. And so it says, how many moles of oxygen are required to react with 2 moles of hydrogen? And so in A, if we're basically looking at our equation here. All right, and so whenever we're comparing reactants to products, we always need to compare these terms in terms of moles. All right, so if you want to go from reactants to products and products to reactants, we always have to convert them to moles in some way. And so here, how many moles of oxygen are required to react with 2 moles of hydrogen? So if we have 2 moles of hydrogen, we want to get to moles of oxygen. And so we have to use our chemical reaction here, equation, our balanced reaction. And so in this equation, it says that we want our moles of hydrogen to cancel out, and we want to be left with moles of oxygen. So here in this balanced reaction, it says if we have 2 moles of hydrogen, it reacts with 1 mole of oxygen. And so here we just solve it out, and we have 1 mole of oxygen here. So we're just using the molar-mole ratio, molar-mole factor, but in terms of one compound to another in the chemical reaction. All right, so in B, we're going to do a similar method. All right, if we're given 5.0 moles of oxygen, we want to convert that to moles of hydrogen. And so we want our moles of oxygen to cancel out, and we want to be left with moles of hydrogen. So from our balanced reaction, we saw that 2 moles of hydrogen will react with 1 mole of oxygen. And so if we have 5 moles of oxygen, we would require 10 moles of hydrogen. And then in C, it says how many moles of H2O form when 2.5 moles of oxygen react. So here we have 2.5 moles of oxygen. We want to figure out moles of H2O. So here we want moles of H2O to remain and moles of oxygen to cancel out. So here from our balanced reaction, if we have 1 mole of oxygen, it's going to produce 2 moles of H2O. And so now we just consolidate out and we get 5.0 moles of H2O. All right, and so we'll look at 6.49. It's something similar. And so we just have a different chemical reaction now. And so here we have, we're looking to go from moles of SO2. We have 0.500 moles of SO2. We want to get the moles of carbon. And so again, we're going to use the balanced reaction. So we want moles of carbon to remain, moles of SO2 to cancel out. So here, in the balanced reaction, it says 5 moles of carbon will react with 2 moles of SO2. And so we just have to do the math now. And we get 1.25 moles of carbon. In B, it says we have 1.2 moles of carbon. It wants us to figure out how many moles of CO. And so in our balanced reaction, it says that if we have 5 moles of carbon, it's going to make 4 moles of carbon monoxide. And we get 0.96 moles of CO. Again in C, How many moles of SO2 are required to produce 0.5 moles of CS2? So we have 0.5 moles of CS2 going to be made. We want to figure out how many moles of SO2 are required. And so from our balanced reaction, we see that when we make 1 mole of CS2, we need 2 moles of SO2. And so here we get 1 mole of SO2. And part D is done in a similar way. And so this is where it all comes together in 6.51. And so here we're given grams, and we need to figure out grams of another reactant or a product. And in order to go from the reactant to products, we always need to bring it back to the number of moles. And so it's a little bit more in depth. And so in A, it asks us to figure out how many grams of Na2O are produced when 57.5 grams of Na reacts. And so how I would do this is I'm going to show you a method that kind of maps it all out. So here we have 4 sodiums plus O2 going to Na2O. We're given the grams of sodium. We need to get the grams of Na2O, sodium oxide. So we first need to go and figure out how many moles of Na. Then we can get how many moles of Na2O, sodium oxide. Then we can go back up to grams of sodium oxide. So here we need to use the molar mass of sodium. Here we need to use the mole ratio to go from 1 mole to another mole. And then here we're going to use the molar mass of sodium oxide. And keeping that in our mind, we'll do out the work here. So 57.5 grams of. So given the 57.5 grams of sodium, we're going to use the molar mass of sodium to figure out how many moles of sodium we have. So in 1 mole of sodium, we use our periodic table, and we find that it's 22.990 grams. And so we just solve this out. And we get 2.50 moles of sodium. And now, looking back at our little map, we got our moles of sodium. Now we need to use our mole ratio to figure out moles of sodium oxide. So we have 2.5 moles of sodium. We want to determine moles of sodium oxide. Want moles of sodium to cancel out. And looking at our balanced reaction, we find that 4 moles of sodium are required to make 2 moles of sodium oxide. And so that would give us a value of 1.25 moles of Na2O. And then now we have 1.25 moles of sodium oxide. We want to figure out how many grams of sodium oxide we have. And so we need to figure out the molar mass of sodium oxide. And so we'll just do that on a separate piece of paper. So Na is 22.99. We have 2 of them. And that will equal 45.98. And then we have the 15.999 of oxygen. And we get 61.979 grams per mole. And so we have, in 1 mole, we have 61.979 grams. And we get a mass of 77.47. Well, I guess we can only put 3 significant figures, 77.3 grams of sodium oxide. Okay, we can do another one in B. So B, it's asking if we have 18 grams of sodium, how many grams of oxygen are required? And so similarly, all right, if we're going to go from sodium, we've got to get moles of sodium. Then we're going to use a different molar-mole ratio and then use the molar mass of O2 to get the grams of O2. And so here we have 18.0 grams of sodium. So in 1 mole of sodium, we have already found that it has a mass of 22.99 grams. And so that gives us a value of 0.783 moles of sodium. Then we have 7.783 moles of sodium. We need to use our mole-to-mole ratio for moles of oxygen. So moles of oxygen is what we're looking for. We want moles of sodium to cancel out. So using our balanced reaction, we see that 4 moles of sodium will react with 1 mole of oxygen. And so we have to divide our moles of sodium by 4. And we get a value of 0.196 moles of oxygen. And so if we have 0.196 moles of oxygen, we need to figure out grams of oxygen. So in 1 mole of oxygen gas, it would have a mass of 31.998 grams. And we get a value of 6.27 grams of oxygen gas. And then C would be done in a similar way. And so I hope that has made things clear. And if you have any questions, just email me, and I'll try my best to lead you in the right direction.